Memory. How do we make it? How do we store it? How do we use it? At SKhainic's, memory, making it, storing it, and using it is our business.
It started in 1946 with the Williams-Kilburn tube, a memory solution formed of a cathode ray vacuum tube, which used streams of electrons to imprint bits of data on the screen.
In 1968, it looked something like this.
The third major characteristic of these machines is speed combined with accuracy. Instructions and data stored on this rotating magnetic drum can be selected by the machine in a few thousandths of a second, or can be selected from these magnetic cores in a few millionths of a second.
Today, this entire process can be replicated on random access memory, or RAM, and read-only memory, or ROM. There are several types of RAM, including DRAM and SRAM. There are also several types of ROM, including NOR flash and NAND flash. Both of these computer memories play key roles in the technology that touches our everyday lives. In the 80s, SKhainic's made its name with the production of an impressive DRAM technology capable of storing up to 256 kilobit DRAMs, a groundbreaking figure at the time. Over the years, the industry has gone through a number of singularities, such as the World Wide Web Internet revolution and the appearance of smartphone technologies. The data generated annually is doubling every 2 years. Today, nearly everything we do requires memory. We live in a high-content, high-speed world. In the not-so-distant future, SKhainic's products will continue to define the next generation of technology. We'll define how AI products expand their thinking and learning. We'll process 5G speeds to help connect cities and countries like never before. We'll help autonomous vehicles process information as they learn new roads and situations. We'll enable expansive augmented reality to discover new worlds. We'll lift communities out of the dark by bringing big data to light. We're prepared to take our expertise to the next level as consumer demands grow and expand. Memory isn't new to SKhainics, it's our specialty.
Hello, I'm Seok Lee, President and CEO of SKhainics. First of all, I'd like to thank the organizing committee for inviting me to this highly prestigious conference, IRPS. I'm a technologist by training, so I'm deeply honored to be here. Today, I'd like to talk about the memory's journey towards the future information and communications technology world. From the next slide, I will use the word ICT as an abbreviation of the information and communications technology because it's too long to say the whole thing. I'd like to highlight some of the changes taking place in the ICT technology and industry and pinpoint some of the key drivers of memory industry. Then I will share my view on the future direction of the semiconductor industry. Let's take a look at the changes in the current ICT environment. We are in the fourth industrial revolution. As we go through the digital transformation, words like smartphone, autonomous cars, smart factory does not seem foreign to us. Living under the impact of the COVID-19 is quite frustrating, isn't it? I do hope that soon we could overcome the difficulties of this pandemic and get together without masks. As the pandemic has impact on our daily lives, some of you might wonder as to what impact it has on digital transformation. This slide makes a comparison of data usage between 2019 and 2020. The COVID-19 pandemic, which started at the end of 2019, gave rise to non-face-to-face activities, such as ICT-based remote learning, work from home in our daily lives, resulting in a spike in data usage. So, as you can see, the COVID-19 has accelerated the ongoing digital transformation in the fourth industrial revolution. I believe the first ICT that comes to our mind is 5G communication. 5G technology enables us the delivery of a large amount of data with high accuracy and speed, which is 10 to 100 times faster than 4G technology. With a diverse range of mobile devices that became available to us, we are able to experience this technology firsthand. And this change is sending ripples across the entire ICT industry. Another game changer along with 5G technology is autonomous vehicle or autonomous car. It has been the subject of many movies envisioning the future, and it is the one that we hope to see happening in the ICT world. Autonomous car is more than just a means of transportation. For autonomous driving, the car should be able to receive, analyze, convert, and feedback the data from various sensors, such as cameras, radar, and LiDAR. So, to enable autonomous driving, a single car is expected to generate more than 4 terabytes of data per day. In both 5G and autonomous cars, the amount of data that is generated and consumed in a real-time basis is expected to increase. As the amount of structured data created and stored in various electronic devices that we use increases, the amount of unstructured data is expected to increase as well. Unpredictable, unstructured data is created and consumed in machine-to-machine communication, including vehicle-to-vehicle communication, along with real-time data streaming and social networking services. So the total amount of both structured and unstructured data is expected to increase exponentially. To handle the explosive growth of data, the compound annual growth rate of data centers around the world is expected to reach 15%, and the data center market is expected to double by 2025. Moreover, if you look at the capacity requirement of DRAM and NAND flash for each data center, the numbers are daunting. As you can see, with the explosive data center growth, the demand for memory and storage essential to data centers will inevitably increase. Therefore, I think that semiconductor memory will become more important in the future. With the digital transformation reshaping our lives, the role of memory will no doubt expand. In the past, memory was used in servers or PCs or cell phones with basic functions. And the function of memory was simple. However, as I mentioned previously, due to the ongoing changes, the function of memory itself is becoming more diverse. So in the near future, the role of semiconductor memory is going to play a more central role in the ICT world, expanding from simple information storage and processing. Now, I'd like to discuss what the new factors that drive the memory industry are and how those factors will reshape the industry. So far, high density, high speed, low power was required of memory to satisfy the need of various applications and customers. Achieving these three requirements is not an easy task. But now, on top of those requirements, high reliability is required in growing markets for smart ICT technology, such as autonomous cars and smart healthcare, where the components are expected to run for a long period of time under extreme conditions. So, reliability will become one of the major requirements. With mounting environmental challenges posing serious threats to the society, I believe that it is time for the semiconductor industry to respond to environmental issues related to energy and show our commitment to social responsibility to make a better place to live in. In the past, the requirements I just mentioned drove the semiconductor industry. In the era of digital transformation, I believe 3S, scaling value, social value, and smart value, will drive the semiconductor industry. So, let me explain what we would need to do for realizing each of these values. First, let's look at the scaling value and look at what we have done to overcome the limitations of scaling. DRAM technology continued to overcome the limitation of geometric scaling and meet the industry required speed and density. From 20 nanometer class in 2012, scaling continued to 10 nanometer class from 2017, and performance improved from DDR4 to DDR5. DDR5 is the next generation DRAM specification for high speed, high density products optimized for big data, AI, and machine learning. The data transfer rate of the first generation DDR5 DRAM reached 4800 megabps to 5600 megabps, which is 1.8 times faster than its previous generation DDR4. In the near future, the maximum transfer rate of DDR5 will be more than 6400 megabps. Also, the error correction code, or ECC, is embedded inside the DRAM chip to self-correct errors down to a single bit level in DRAM cells. So, we believe the reliability of the system will improve by approximately 20 times. SKhainicks also contributed to the development of DRAM technology by developing, launching DDR5 for the first time in the industry. Currently, to overcome the limitation of further scaling in DRAM, we are focused on three areas: overcoming the limitation of patterning in lithography, maintaining the capacitance of the cell capacitor, and lowering the resistance of the metal for interconnect. Lowering the resistance of the interconnect, this is not a new item. In logic technology, it has been an issue for more than 10 years. Now, it's getting into memory. First, to overcome the limitation of lithography, we adopted EUV technology. To secure a stable EUV patterning performance and enhance the productivity, we are controlling materials and defects in addition to developing photoresist materials, working with partners. Second, in regards to the cell capacitor, we continue to overcome difficulties with innovation in new material and structure to maintain cell capacitance, which becomes smaller as dielectric thickness scaling continues. If you don't know what the DRAM is, simply say DRAM consists of one transistor and one capacitor. So the amount of charge you store in the capacitor is the key for the successful DRAM device. Last, in regards to the low resistance metal for interconnect, we continue to overcome the challenge by introducing next generation electrode and insulating materials and new processes. One of the most significant challenges that poses a threat to DRAM reliability is software error, especially for automotive application where high reliability is required. Responding to software error is all the more important. To increase immunity against the software error, design option is usually considered, but as it entails area penalty, cost increase is inevitable. In SKhainicks, we were able to overcome this challenge with extreme engineering, such as well structure and junction size optimization in order to achieve both software rate, immunity, and cost objectives. So I like to emphasize that solution to any problem is not just one. Next, I'd like to talk about NAND flash. After transitioning from 2D to 3D structure in 2015, with the successful development of 96-layer 4D NAND in 2018, NAND technology development continues with the goal of achieving high capacity by overcoming the limitation of stacking. In 2020, SKhainicks successfully developed the industry's most multi-layered 176-layer 4D NAND, building upon the technology leadership. In NAND, there are three key challenges we continue to face. Those are securing high aspect ratio contact etch technology, securing cell dielectric characteristics, and solving film stress issues. Currently, we came up with a 4D NAND stacking to continue to achieve the industry-required high density. But to further enable stacking, high aspect ratio contact technology is required. Therefore, with partners, we plan to improve the equipment performance and come up with innovation in materials. Also, we will innovate structures of high aspect ratio contact etch technology to enable further stacking. Second, to secure cell dielectric characteristics, we are using ALD, atomic layer deposition technology. This technology allows a fast and uniform deposition of different types of materials in a small plug, and with the innovation in dielectric material, we are also using the technology of trapping and maintaining a certain amount of electric charge. Last challenge is reducing the film stress of NAND. To minimize film stress from causing wafer bending and warpage, current solution used is to control the mechanical stress levels of films and optimize the cell oxide and nitride material. On this slide, I will give you an overview of NAND reliability challenge in oxide nitride scaling. I will call it, simply say, ON scaling. The left-hand side graph shows the lateral charge loss becoming larger compared to the vertical charge loss as the oxide nitride or ON scaling continues. So one of the most critical challenges to overcome in NAND reliability is the lateral charge loss in ON pitch scaling. To improve the lateral charge spreading, SKhainix, we have developed a deep trap, charge trap nitride, or CTN, and an isolated CTN structure in which CTN layer is cut off between the cells. If you think about 10 years from now, we can expect challenges requiring a change in the technology to continue scaling DRAM below 10 nanometer and stacking NAND above 600 layers. SKhainix will overcome those challenges by innovation in material and structure, solving reliability issues. In other words, bringing innovative technology to further scaling in DRAM and stacking in NAND. After all, the ultimate value that scaling offers is responding to the need of the industry and customers. In this chapter, the value pursued by the word social means addressing social needs such as energy, disease, and environmental issues besides creating economic values. Recent global climate change is occurring at an accelerating pace. Graph on the left shows the global temperature change, and it means that 1 degree in Celsius increase in the average temperature brings much more frequent killer heat waves. In light of this situation, many countries around the world, including Europe, US, China, have declared net zero targets to reduce CO2 emissions, the main culprit of global warming. The EU pledges to cut greenhouse gas emissions to net zero by 2050. And the energy sector, which runs on fossil fuels, faces increasing pressure to curb CO2 emissions. Imagine what it would be to change all the hard disk drives in the world to SSDs. Doing so will be equivalent to reducing CO2 emissions by almost 93%. Then, what would it be like if we were to replace hard disk drives of all the data centers around the world with low power PLC or QLC based SSDs by 2030s? PLC is it stands for penta-level cell, which means you put 5 levels of information in a one cell. So it's more cost efficient. By doing so, we can reduce CO2 emissions by staggering 41 million tons based on BAU, and also create more than approximately $3.8 billion worth of social value. Due to the ongoing global climate change and the COVID-19 pandemic, there is an increasing social demand for a low-power product capable of transferring massive workloads at higher data transfer rate than before. Then, would it be possible to meet the requirement of the ICT society with a conventional scaling? Maybe not. Although we try to meet the requirement of the ICT society, I believe the speed of memory technology development is yet to catch up with the demand, and such gap is expected to widen with time. With the explosive growth of data, there will be an overwhelming amount of data to compute. But the existing computing memory is not able to support the computation of such large quantities of data. So, to overcome the existing limitation, changes in the computing and memory hierarchy are taking place. The architecture of the CPU is evolving into multi-core, many-core, and heterogeneous computing. Also in memory, along with increasing demand for both high capacity and high speed memory, there is also a demand for heterogeneous memory, which is specialized for either high capacity or high speed. There are representative examples of heterogeneous memory solutions. First solution is high bandwidth memory, delivering high bandwidth, as the name says. It is optimized for AI and high performance computing. Second is the ultra low power memory. It is high density memory compared to cache and has a significantly better power efficiency compared to the existing memory. Last is the emerging interface solution called CXL, stands for Compute Express Link. CXL memory is being prepared as a solution that not only expands bandwidth and capacity, but also realizes the value of a persistent memory, enhancing the reliability of a memory. I believe this will become a solution to narrow the gap between the memory performance and the industry requirements. As I mentioned, SKhainic's has continued to develop and deliver various solutions, meeting various speed, capacity, and power requirements of the ICT society. And we will continue to do so in the future. Also, our efforts to incorporate social responsibility into technology development do not end here. For us to continue to live in this beautiful planet Earth, I cannot emphasize enough the need to solve the energy issues. The orange line in this slide is the limit of total energy production in the world based on an assumption. If we were to follow the current path based on the current solution alone, soon we will reach the first critical point. So to delay reaching the critical point, convergence solutions suitable for each era should be delivered, not only to greatly reduce the energy consumption in computing, but also to improve the computing performance. In the next part of my presentation, I will talk about the smart solution designed to deliver effective computation technology. The future world will be a hyper-connected world characterized by low power consumption, where all the societies are connected at an unprecedented rate thanks to the convergence of semiconductor, AI, and communications technology. Past was the digital age, where each electronic device evolved into a different form. But now, we are transitioning to the era of digital transformation, where all the devices are connected. And the future will be the era of new ICT, where all the devices are integrated with the AI technology. Aligned to such development, there should be a revolutionary change which transcends boundaries in the semiconductor memory. I think the value that reflects this future world is smart. So we will do our best to develop technologies to prepare for memory transformation for new ICT era after digital transformation. Also, we will strive to incorporate smart value into intelligent memory solutions that we deliver. If you think about the technology development beyond the next 10 years, the era of convergence where memories are converged with CPU and storage will come. And in post-von Neumann computing era, even the boundaries between the CPU and the memory and between the memory and storage will cease to exist. At this point, revolutionary technology such as neuromorphic computing will be required. In the era of convergence, to overcome the limitation of memory performance, there will be a convergence of memory and logic. The concept is to add a few computing functions of CPU to DRAM. As the speed was increased in HBM or high bandwidth memory by increasing the number of channels between the CPU and the memory, the speed will increase further in PNM, processing near memory, where both CPU and the memory exist within a single module. The speed will further increase in PIM, processing in memory, where the CPU and the memory exist within a single package. And ultimately, the speed will increase further in CIM, computing in memory, where the CPU and the memory is integrated within a single die to deliver high-performance computing system. The memory device and storage technology of the post-von Neumann computing era will evolve to neuromorphic memory and DNA storage type of technology. If so, ultra-high-speed computation and storage will become possible even with small amount of the energy human brain uses. Also, it will become possible to enable a true smart world where the same large amount of data can be stored and processed at low power in a small room without having to maintain 100,000 square meters of data centers. SKhainicks is preparing for the future by taking the evolutionary path and the revolutionary path to respond to changes in semiconductor memories. Through a rigorous research and development, we will continue to incorporate the value of scaling in the conventional memory to include social value in the next generation, memory and intelligent memory, and to contain the value of smart in the post-von Neumann era. Considering the ongoing digital transformation, I also think that the semiconductor industry itself should transform. If we think about the characteristics of the semiconductor industry, it has been equipment, technology, capital, and knowledge-intensive industry. And so far, we were able to overcome technology limitations. However, due to such characteristics of industry, it is becoming increasingly difficult to develop technologies. Scaling sub-10 nanometer class, dealing with increased number of process steps, and more than 2 months of prolonged turnaround time, and dealing with spikes in development cost are some of the many challenges we face. All requires consideration of technology, productivity, and development cost, but none of them are easy to solve alone. This is why I think transformation is needed in the semiconductor industry. In the past, scaling competition among semiconductor companies and vertical collaboration with suppliers helped solve problems of technology, completeness, and productivity. But now, we face an era where we have to deliver not only scaling value, but also social and smart value. To make this possible, I think various partners that form the ecosystem of the semiconductor industry should collaborate with one another. Only by establishing a strategic partnership for open innovation based on collaboration and sharing with customers, suppliers, academia, and government, we can shape a new era which pursues both economic and social value. SK하이닉스 will take the initiative in enhancing the quality of our lives, solving environmental issues, and pursuing the happiness of our employees and stakeholders. We will incorporate scaling, social, and smart value to technology development to achieve the ultimate goal of making a better ICT world. We ask for your interest, support, and hopefully your participation in pursuing social values and actively responding to the need of the era with technology. Thank you.
Semiconductors connect our homes to other homes and cities to other cities. Whether it's 5G connectivity, IoT capabilities, augmented reality, virtual reality, or artificial intelligence, semiconductor memory is already deeply embedded in our everyday lives. In cities around the world, these memory-enabled technologies keep our lives running at lightning-fast speeds, helping autonomous vehicles process information and make split-second decisions as they learn new roads and situations. Expanding how AI products think and learn to make our lives more convenient and get us the things we need even faster. Building networks of smart cities and hospitals through IoT's enhanced data depth. Lifting communities out of the dark by bringing big data to light. And discovering new worlds through augmented reality. Whether it's for work, with virtually enhanced meeting experiences that can transport you around the world, or for fun, with virtual fitting appointments and meals delivered by memory-enabled robots, or even for security, with cutting-edge facial recognition technologies that allow you to use your face as a password on devices, from your smartphone to your home security system. These technologies and the semiconductor memories that support them are leading the way towards the smart cities of tomorrow. And by creating the memory solutions of the future, SKhainix is taking us there.